Hi, we are going to look at the reactions of carboxylic acid derivatives. We learned in chapter 19 the reactions at aldehydes and ketones. Those two undergo nucleophilic addition by the mechanism shown below. We had this mechanism several times in chapter 19. So nucleophile adds to the carbonyl carbon, and H+, which is an electrophile, adds to the oxygen. Carboxylic acid derivatives also contains the carbonyl group. So we expect them to undergo nucleophilic addition, but they undergo nucleophilic substitution different by the mechanism here. Same nucleophile, it adds to the carbonyl carbon and flips the bond. The next we expect it to actually pick up a proton and form an alcohol. That is not happening. Instead of it, the negative charge returns the electrons and pushes this out. So the Y group in carboxylic acid derivatives left as a Y minus. So we substituted the Y group with a nucleophile. So it is a nucleophilic substitution. We had to tell the reason why aldehydes undergo addition while this carboxylic acid undergoes substitution. The reason is pretty simple. If it is a ketone, R prime is an alkyl group. If it is an aldehyde, it is a hydrogen. These are not living groups. If a group is not a living group, you cannot substitute it. But here, the Y groups in carboxylic acid derivatives, living group. So you can substitute them, you see. That's the reason. I put them in words here, you can read it. So the point is all carboxylic acid derivatives undergo nucleophilic substitution. But if you compare the reactivity, some reacts slower, some reacts faster of the four. Which reacts faster? Acid halides are the most reactive. Then comes anhydrides. Then the esters. The amides are the least reactive. Why? All the four are reactive, but some of them is very reactive, some of them are not. What is the reason? It is because of the resonance. In all the four, the Y group has one or more lone pairs. So this resonance is possible. What is the result of this resonance? Number one, resonance stabilizes the molecule. The second, it decreases the amount of positive charge on the oxygen, carbonyl carbon, because of the resonance. So the resonance has two effects. It stabilizes the molecule. It diminishes the partially positive charge of the carbonyl carbon. Both of them decrease the reactivity. More stable molecules are less reactive. If the amount of positive charge of the carbonyl carbon is less, its reactivity is less. But the amount of resonance, some resonate faster, some resonate slower. So less the resonance, more the reactivity. Why? Look at those four: acid halides, anhydrides, esters, and amides. The Y group in these, I listed them here. What is YAC group? This is oxygen, and this is the YAC group. This is an AC. So this is the one I wrote it as YAC. In esters, it is OR group. In amides, it is NH2 group. Of the four groups, the halogen and YAC group or electron withdrawing groups, the OR group and NH2 group or electron releasing groups. Among the two electron withdrawing group, halogen is more electron withdrawing group than YAC group. Among the two electron releasing groups, NH2 is more electron releasing than OR group. So what? The amount of resonance increases, more the electron releasing capability. If it is electron withdrawing group, the resonance is less stable. Suppose you look at it here, don't write. If it is an electron withdrawing group, it hesitates to put the electron and participate in the resonance. It does, but slow. If it is an electron releasing group, it does it faster. So there is more resonance at the amides than at the acid halides. The resonance makes actually amides the most stable, the acid halides the least stable. There's least stable and also amount of positive charge. If it is less resonance, it is more resonance, it is less. If you combine disaffect and disaffect, less stable, more positive charge at the carbonyl carbon, that means it is the most reactive. More stable, less positive charge at the carbonyl carbon, that is less reactive. So these are the reasons.